let me pull all this together and write it in a very simplified manner. Okay, so what we have here is C transpose KD equals C transpose F. Okay, this is close to the final form of our finite element equations in matrix vector form. Okay, but there's one other important step we need to take here, which is to recognize that this vector of weighting function degrees of freedom actually does interpolate the weighting function, right? So recall that in each element we had WH of E equals sum over A, NA, CAE, going back just briefly, momentarily actually, to our local element numbering system for the C degrees of freedom. Okay? Also recall that our weak form, our statement of the weak form is the following, right? In a much abbreviated version, it was to find UH belonging to S such that, ST is short for such that, for all WH belonging to V, and I'm sorry, these are both, that's SH and VH, right? For all WH belonging to VH, the following integral holds, the following equation holds, right? So this is our weak form again, yet again. Okay. What we've done now is essentially reduce that integral weak form to the equation at the top of the slide, okay, in matrix vector form, right? So, and let me yet again state that here, okay? All these statements, while a little superfluous, are repetitive definitely, are useful to drive home points, so we make them repeatedly. All right, so that is our matrix vector weak form, and the important thing that I want to point out is that this holds for all WH belong to VH. My question to you now is that what is it in the matrix vector weak form that represents WH? Remember, using basis functions, finite dimensional basis functions, we've gone from this integral form at the bottom of the slide, the last equation on the slide, which involved fields, to the matrix vector form, which involves just degrees of freedom for matrices, for vectors, and we have entries for matrices. So in that setting, what is it that represents WH? Okay. Essentially, what represents WH is the following. This equation of ours is completely equivalent to our statement at the top of the slide, C transpose KD equals C transpose F, when we realize that this has to hold for all C, right, belonging to this R NEL space. Right? C, after all, is just a vector with NEL entries. Okay, it is when we specify that our matrix vector weak form must hold for all C, right? Because all C belonging to this NEL degree of this NEL dimensional space, that we are essentially imposing the same requirement as we do here. And why is this? It is because the C's are just degrees of freedom which interpolate the weighting functions. If our weak form has to hold for all weighting functions belonging to VH, we've already fixed the functional form of VH by choosing particular polynomial basis functions, right, or by choosing certain basis functions. that degree of arbitrariness which must still hold within the space VH is ensured if we require that the matrix vector weak form holds for all C belonging to this NEL dimensional space. Okay? Well, but if this is the case, it is clear, therefore, that this can only hold if KD equals F. There is a formal way of demonstrating that, and this just involves moving everything to the left-hand side and then considering what forms C can possibly have, all the forms that C can possibly have, and discovering that this must be the case. Okay? We can make that rigorous argument if we need to, but I think it's pretty clear why this works. Okay? So this is the final form of our finite element equations. Okay? FE short for finite element. Right? Remarks. Okay. The first remark I want to make is that the matrix K that you have in front of you or in your notes is symmetric it's positive definite. Okay. Furthermore, it has a banded so-called tridiagonal structure with banded tridiagonal structure. Okay. The symmetry comes from the fact that the term in the weak form which gave rise to our matrix K has this sort of structure. Right, where this is our stress. Okay, so if you look at this integral as an object called a functional in W and U, it is bilinear. Okay, furthermore, it remains unchanged if we just swap the places of W and U. Okay. Right, so the reason this thing is symmetric is because we have this term in the weak form, and we could very well interchange those two positions, right? WH and UH. Okay, this is what makes our final K matrix symmetric as well. If we were working with a different set of equations which for some reason did not give us this form of an integral where WH and UH could be interchanged and still have the same meaning, right, and still have the same integral, then we would not have a symmetric matrix K. Okay. Oh, of course, I should also state that now K, again for obvious reasons, is called the stiffness matrix. Okay, and as you might imagine, this is related to the fact that when we look at it in the form KD equals F, which you have before you, it is reminiscent of a spring, right? K being the spring stiffness, D being the displacement of the spring, and F being the force in the spring. And indeed, in the early days of finite elements, when there was a lot of structural mechanics work done with finite elements, this was the right interpretation. Okay, but now if you imagine that you're doing a heat conduction problem, we would probably properly call it something else, maybe the conductivity matrix, right? But traditionally it's called the stiffness matrix. So let me just put that in quotes. Okay. Now, the other bit is the positive definiteness. The positive definiteness comes from the fact that our, in this particular case, our so-called material constant E is greater than 0. We didn't actually state that, but if E indeed is greater than 0, then we have a positive definite system. All right. The particular banded tridiagonal structure comes from the fact that there are two first order derivatives and that we have a linear set of basis functions. Okay. So well, no, the bandedness is actually is included when I say tridiagonal. So tridiagonal from single derivative on WH and UH, right, in this form that's before us in the integral. Okay, there's a single derivative on each of them, and from the fact that we have linear basis functions. Okay. The next remark I want to make, and really it's the final remark of this segment, it is the fact that our force vector in this case, I'm just looking back to my notes here to make sure that I have, there we go, that I have it before me so I don't make any errors in putting it back up here. Okay, our force vector in this case is the following. It's FA HE over 2 times 2 going all the way down to 1 plus 0 all the way down to TA in the last entry plus EA over HE multiplying our Dirichlet boundary condition U0 and zeros all the way down. All right. There are a few things I want to point out about this. If we look at this contribution to the force term, it comes from the distributed forcing function that was specified at every point along the bar, right? Our original function f, right, which we assume is a constant in order to get this final form. If f were not a constant, it would be inside this, it would be within this, the column vector here. Okay. So one thing to note is that if we consider the mesh and consider a stretch of the mesh with elements of that type, okay, what we are seeing is that the contribution on a node which has elements on either side of it is of the form FAHE. Okay. It's only the very last element, right? This is the point L, okay? It's only this very last element which has a contribution this very last node which has a contribution FAHE over 2, okay? And this is really because an interior node has a contribution FAHE. It sort of has the entire force on it because it has elements on both sides, so both those elements contribute force to it. However, this last node has a contribution only from the element to its left. Okay. This is pretty obvious. This contribution is from the traction, and it's no surprise that it appears only on the very last node because that's where the traction is indeed applied. This contribution is also a very important one. you recall that this came about from the fact that the Dirichlet boundary condition is known, and therefore that degree of freedom in the D vector in our trial solution vector could be moved over to the right hand side. Dirichlet BC for boundary condition. Okay, so what this is giving us is the loading, right, on the problem obtained by specifying a Dirichlet boundary condition. Okay, so this is what you may call, within quotes, the Dirichlet driven load, right? We all very well know that partial differential equations can be driven by either Dirichlet or Neumann boundary conditions. This is how the Dirichlet boundary condition itself drives the problem. Of course, in the kinds of problems we are considering, the sort of boundary value problem we are considering, U0 was typically 0. Okay, so that actually drops out. But in the context of elasticity, what it does for us is give us the effect of the load that gets transmitted to the structure, because of the fact that on the left end, at the left end of the structure, we've fixed the displacement to be equal to 0. Okay. So let me just say one more thing here. This Dirichlet driven load is equal to 0 in the considered case. Okay, so there we have it, the various contributions to the effective forcing on the problem coming from the distributed forcing function, from the traction, the Neumann boundary condition, right? Since I'm calling it traction, I also ought to say that this is the Neumann boundary condition, and finally the effect of the Dirichlet boundary condition as well. Okay, we will stop this segment here, but essentially at this point we have completed our simplest finite element problem in 1D for linear elliptic equations. Okay, well, I should also state one more thing, right? I've just formulated the problem. What is the solution? Since we have KD equals F, the solution is D equals K inverse F. Okay, that is the formal solution. Of course, you may or may not actually invert K depending upon the size of your problem. That is an entirely separate question which we don't get into here. This is just the formulation. Once we have D, of course, we can then go back and reconstruct UH in any element as being simply the interpolation over A using the basis functions, which we know very well, times D, A, E. Okay, so we recover the actual field from the solution. Okay, here's where we definitely do stop the segment.